Hello everyone, this is the audio recording for visually impaired students from the book of Physical Chemistry of Pradeep. Here we will read about colloidal states of matter. Article 7.1 Colloidal states of matter. Thomas Graham studied the rate of diffusion of liquids and solutions across the animal membranes, and as a result of his experiments he divided the soluble substances into two classes. First, crystalloids, second, colloids. The substances like common salt, sugar, urea, etc., which can be obtained in the crystalline form and in the dissolved state diffused through the vegetable or animal membrane, were termed as crystalloids, and the substances like starch, gum, glue, etc., which are non-crystalline in nature and in the dissolved state do not diffuse or have a little tendency to pass through the animal or vegetable membrane, were given the name colloids. Graham's classification of substances into crystalloids and colloids was soon proved to be wrong. A crystalloid was found to behave as a colloidal under different set of conditions and vice versa. For example, sodium chloride behaves as a crystalloid when dissolved in water but behaves as a colloid when dispersed in benzene. It has since then been realized that a clear-cut difference does not exist between crystalloids and colloids. The non-diffusibility of colloids and diffusibility of crystalloids through the animal or vegetable membrane was shown to be due to the difference in the size of particles of crystalloids and colloids. The colloids from bigger particles which cannot pass through the membrane. It is therefore preferable to speak of a substance in colloidal state rather than calling it a crystalloid or a colloid. The particle state limits are given below. Size and diameters of particles. True solution less than 10 raised to power 9 or 1 nanometer. Colloidal solutions between 10 raised to power minus 9 and 10 raised to power minus 7 meter, or 1 nanometer to 100 nanometer, that is 10 angstroms to 100 angstrom. Suspensions more than 10 raised to power minus 7 meter or 100 nanometer, that is greater than 1000 angstrom. Thus, the size of the colloidal particles is intermediate between that of particles of true solution and those of suspension. A colloidal solution of matter is therefore a state in which the size of the particle that can pass through filter paper but not through animal or vegetable membrane. Thus, every substance can be brought into colloidal state by adopting suitable methods. The distinction between characteristics of true solution, colloidal solution, and suspension is given in Table 7.1. Table 7.1 Characteristics of true solutions, colloidal solution, and suspension. So, first property is particle size. True solution have less than 10 raised to power minus 9 meter or 1 nanometer. True solution pass through ordinary filter paper as well as animal membrane. They do not settle. Particles are invisible in this. They diffuse quickly. They are clear and transparent. Particle size of colloidal solution is between 10 raised to power minus 9 to 10 raised to power minus 7 meter. They pass through ordinary filter paper but not through animal membrane. They do not settle. This scattering of light by the particle is observed under ultramicroscopy. They diffuse slowly. They are translucent in nature. The particle size of suspension is more than 10 raised to power minus 7 meter or 100 nanometer. They do not pass through filter paper and animal membrane. They settling on sand links. Particles are visible to naked eyes or under a microscope. They do not diffuse. They are opaque in nature. A simple example to understand a true solution, a suspension, and a colloidal solution is to consider the solution of sugar in water and that of water in which mud is stirred. The former is a true solution, but in the case of the latter, so long as the stirring is continued, the mud remains in suspension, but as long as the stirring is stopped, the large particles fall to the bottom of the vessel. However, smaller particles remain in suspension for a longer time. This part of water containing minute and particles which cannot be seen even under microscope and pass through the filter paper is a colloidal solution. Article 7.2 Types of colloidal systems. Just as in a true solution, the substance dissolved is called the solute and the medium in which it is dissolved is called the solvent. Similarly, in a colloidal system, the term solute and solvent are replaced by the terms dispersed phase and dispersion medium respectively. Thus, Thus, dispersed phase means the substance distributed in the dispersion medium in the form of colloidal particles, and the dispersion medium means the medium in which the substance is dispersed in the form of colloidal particles. The colloidal system thus obtained is sometimes called a colloidal dispersion or a dispersed system. Evidently, unlike a true solution which is homogeneous, a colloidal system is heterogeneous, consisting of two phases, the dispersed phase and dispersed medium. Depending upon whether the dispersed phase and dispersed medium are solid, liquid or gases, 8 types of colloidal systems are possible. A gas mixed with another gas forms a homogeneous mixture are not a colloidal system. The example of the various types along with their typical names are listed in Table 7.2. Table 7.2 Types of colloidal systems or colloidal dispersion. Dispersion phase, dispersion medium, name and example. Solid in solid, solid state. Example, some colored glasses. Solid in liquid, sol. Some paints, muddy water. Solid in gas, aerosol, smoke, dust. Liquid in solid, gel. Cheese, butter, jellies. Liquid in liquid, emulsion. Milk, hair cream. Liquid in gas, aerosol, fog, mist, cloud. Gas in solid, solid form, pumice stone, foam rubber. Gas in liquid form, froth, wiped cream. Out of the various types of colloidal system listed in the table 7.2, the most common are sols, gels and emulsions. Further, it may be mentioned that depending upon the dispersion medium, the sols are given species name as follows: water, aquasol or hydrosol; alcohol, alkosol; benzene, benzosol; gases, aerosol. Classification of colloids or colloidal sols. The various substances which form colloidal sols are divided into two categories, namely lithophobic and lyophobic. If water is the dispersion medium, the terms used are hydrophilic and hydrophobic. First, lyophilic colloids. The word lyophilic means liquid loving. Substances like gum, gelatin, starch, rubber, etc., which when mixed with a suitable liquid as the dispersion medium directly form the colloidal sol or called lyophobic, and the sols thus obtained are called lyophilic sols. As they form the colloidal sol directly, they are also called intrinsic colloids. An important characteristic of these sols is that if the dispersed phase is separated from the dispersion medium, the sol can be made again by simply remixing with the dispersion medium. That is why these sols are also called reversible sols. Further, these sols are quite stable and cannot be easily precipitated. Lyophobic colloids. The word lyophobic means liquid hating. Substances like metals, their sulfides, etc., when simply mixed with a dispersion medium, do not form the colloidal sol. Their colloidal sols can be prepared only by special methods. Such substances are called lyophobic, and the sols formed by them are called lyophobic sols. As their colloidal sols have to be prepared by indirect methods, they are also called extrinsic colloids. These sols are readily precipitated and hence are not stable. Further, once precipitated, they do not give back to colloidal sols by simply addition of the dispersion medium. Hence, these sols are also called irreversible sols. The greater stability of the lyophobic colloidal sols than the lyophobic colloidal sols is due to the fact that the former are highly hydrated in the solution. The essential points of difference between lyophobic sols and lyophobic sols are given in table. Points of difference between lyophilic and lyophobic sols. In lyophobic sols, prepared easily by direct mixing with the liquid dispersion medium, they are quite stable and are not easily precipitated or coagulated. They are highly hydrated. They are renewable in nature, that is, once precipitated can reform the colloidal sol by simply remixing with the dispersion medium. These sols are usually formed by the organic substance like starch, gum, proteins, etc. Their viscosity is much higher than that of medium. Their surface tension is usually lower than that of dispersion medium. Their particles are neither visible nor detected easily by the ultramicroscopy by the scattering of light. Their particles may migrate in either direction or may not migrate at all. Lyophobic sols cannot be prepared directly, prepared by special methods only. They are easily precipitated by the addition of a small amount of a suitable electrolyte. They are not much hydrated. They are irreversible in nature, that is, once precipitated cannot form the colloidal salt by simply addition of the dispersant medium. These salts are usually formed by the inorganic materials like metals, their sulfides, etc. Their viscosity is almost the same as that of the medium. Their surface tension is nearly same as that of the dispersant medium. Their particles, though not visible, can be easily detected by an ultramicroscope. Their particles migrate in only one particle direction in the electric field. Article 7.4 Multimolecular, Macromolecular and Associated Colloids. The main characteristics of a colloid is its particular size. When some solid substance is dispersed into a medium in which the solid substance is otherwise insoluble, such that after dispersion the size of the solid particle lies in the colloidal range, the system is called a colloidal dispersion. Examples of colloidal dispersion are gold salt, a colloidal dispersion of As2H3 in water, etc. Depending upon how the different substance may have size in the range of the colloids, the various types of colloids or colloidal dispersion may be divided into the following three categories. First, multimolecular colloids. When on dissociation, a large number of atoms or smaller molecules of a substance aggregate together to form species having size in the colloidal range. The species that formed are called multimolecular colloids. The dispersed phase in this type of colloidal system may contain large aggregates of atoms or molecules formed as a result of aggregating properties of the dispersed particles. For example, a gold salt may contain particles of various sizes having several atoms. Sulfur salt consists of particles containing thousands of or so of Sg sulfur molecules. They are held together by vulnerable force. Second, macromolecular colloids. When certain substances having big size molecules called macromolecule have large molecular masses are dissolved in a suitable liquid, they form a solution in which the molecules of the substance, that is, the dispersed particle, have size in the colloidal range. Such substances are called macromolecular colloids. These macromolecular substances are usually polymers with very high molecular masses. Examples of naturally occurring macromoleculars are starch, cellulose, proteins, enzymes, and gelatin. Examples of man-made macromoleculars are polythenes, nylon, polyester, synthetic rubber, etc. As these molecules have larger sizes and have dimensions compatible to those of colloidal particles, their dispersions are called macromolecular colloids. Their colloid solutions are quite stable and resemble true solution in many aspects. Third, associated colloids. Micelles, the substance which when dissolved in a medium at low concentration behave as normal strong electrolytes but at higher concentration exhibits colloidal state properties due to the formation of aggregated particles are called associated colloids. The aggregate particles thus formed are called micelles. The formation of micelles takes place only above a particular temperature called Kraft temperature (Tk) and above a particular concentration called critical micelle concentration (CMC). The most common example of associated colloids is that of surface active agents such as soaps and synthetic detergents. For soaps, the CMC is 10⁻⁻⁴ to 10⁻⁻³ mole per liter. Each micelle contains at least 100 molecules. Mechanism of micelle formation. Let us take the example of soap solution. Soap is a sodium salt of higher fatty acid and may be represented as CrCOO and A. Example, sodium citrate with CH3CH2 16 COO negative Na positive. When dissolved in water, it dissociates into RCOO negative and Na positive ion. The RCOO negative ion have consist of two parts, that is non-polar long hydrocarbon ring chain R called the tail, which is hydrophobic, and the polar group COO negative called head, which is hydrophilic. The RCOO negative ion are therefore present on the surface with their COO negative groups in water, and the hydrocarbon chains are staying away from it and remain at the surface. However, at higher concentration, these ions do not remain on the surface but are pulled into the bulk of the solution. As a result, at higher concentration, the RCOO negative ions form an oil aggregate with their hydrocarbon chains pointing towards the center and the COO part outward as shown above. An aggregate thus formed is known as ionic micelles. Each of these micelles may contain up to 100 ions. Similarly, in case of detergents, example sodium lauryl sulfide, the polar group is SO42 negative along with the long hydrocarbon chain. Hence, the mechanism of micelle formation is similar to that of the SOPs. It is interesting to add here that CMC micelles are almost spherical at concentration slightly higher than, but to CMC they form flattened surfaces. At still higher concentrations, they form extended parallel sheets 2 molecular thick. These are called lamellar micelles. It was shown for the first time by M.C. Bain by X-ray analysis the existence of plate-like micelles of SOPs. Hence, they are named as M.C. Bain micelles. The comparisons of the main characteristics of the above three types of colloids is given in table 7.4. Multimolecular colloids. They are formed by the aggregation of a large number of atoms or molecules which generally have diameter less than 1 nanometer. Example, soaps of gold, sulfur, etc. Their molecular masses are not very high. Their atomic or molecules are held together by weak van der Waals forces. They usually have lyophilic character. Macromolecular colloids. They are molecules of larger size. Example, starch, proteins, and polymers like rubber, nylon, etc. They have high molecular masses. Due to long chain, the van der Waals forces holding them are comparatively stronger. They usually have lyophilic characters. Associated colloids. They are formed by the aggregation of a large number of ions in concentrated solution. Example, soap solution. Their molecular masses are generally high. Higher is the concentration, greater are the van der Waals forces. Their molecular contain both lyophilic and lyophobic groups. Article 7.5. Preparation of colloidal solutions. As discussed earlier, the lyophobic salts can be prepared directly by mixing the substance with the dispersion medium. For example, colloidal salt of starch, gelatin, gum, Arabic, soaps, etc. are prepared by simply dissolving these substances in warm water. Similarly, a colloidal salt of cellulose nitrate is obtained by dissolving it in an organic solvent such as ethyl alcohol. The product obtained is called colloidation. However, the lyophobic salts cannot be prepared directly, hence the following two types of methods are employed for obtaining the lyophobic salts. A. Dispersion or disintegration method. These methods involve the breaking of the bigger particles to colloidal size. The methods generally employed for this purpose are briefly described below. First, mechanical disintegration. The mechanical disintegration is carried out in a mechanical called colloid mill. It consists of two steel discs with a little gap in between and capable of rotating in the opposite direction at high speed. A suspension of the substance in water is introduced into the mill. The size of suspension particles is reduced to that of the colloidal size. Electro disintegration. This method is employed for obtaining colloidal solutions of metals like silver, gold, platinum, etc. An electric arc is set up between two metallic electrodes suspended in a trough of water. The intense heat of the arc converts the metal into vapors which are considered immediately in the ice cold water bath, resulting in the formation of particles of colloidal salts. Third, precipitation. Precipitation is a process of passing of precipitate into colloidal particles, not adding suitable electrolyte. The electrolyte added is called precipitating agent. A few examples of salts obtained by precipitation are given below. First, the reddish-brown colored colloidal solution is obtained by adding small quantity of ferric chloride solution to the freshly precipitate ferric hydroxide. Second, a precipitate of silver iodide can be precipitated by shaking with a dilute solution of silver nitrate or Ki. Third, on adding insufficient quantity of very dilute HCl solution to the freshly precipitated aluminium hydroxide, a salt of aluminium hydroxide is obtained. Cause of precipitization. As the electrolyte is added to a freshly precipitated substance, the particles of the precipitate preferentially absorb one particular type of ions of the electrolyte and gets dispersed due to the electrolytic repulsion. This gives particles of colloidal size. Freshly prepared precipitates are preferred as they easily peptidized. B. Concentration or aggregation methods. First, by chemical reaction, by double decomposition, when H2S is passed through a dilute solution of arsenic or oxide in water, a colloidal solution of arsenious sulfide is obtained. As2O3 plus 3H2O gives As2S3 plus 3H2O. By reduction, gold, silver, platinum, etc. are obtained in colloidal form by reduction of very dilute solution of their salts with a suitable reducing agents. 2AuCl3 plus 3SnCl2 gives 2Au plus 3SnCl4. Gold salt can also be obtained by reduction of AuCl3 solution with formaldehyde and tannic acid or with hydrazine. 2AuCl3 plus 3HCHO plus 3H2O gives 2Au plus 3HCOOH plus 6HCl. 4AuCl3 plus 3NH2NH2 gives 4Au plus 3M2 plus 12HCl. By oxidation, sulfur is obtained in the colloidal form when H2S is bubbled through the solution of an oxidizing agent like nitric acid, bromine water, etc. S2S plus Br2 gives S plus 2HBr. S2S plus 2HNO3 gives 2H2O plus 2NO2 plus S. By hydrolysis, FeOH3 plus AlO3 salts are obtained by boiling solutions of their corresponding colloids. FeCl3 plus 3H2O gives FeOH3 plus 3HCl. By exchange of solvents, substances like sulfur and phosphorus are fairly soluble in alcohol but less soluble in water. If their alcoholic solution are poured in water, colloidal solution of sulfur and phosphorus are obtained. Third, by condensing vapors of a substance into the solvent. Colloidal solution of sulfur and mercury in water are prepared by passing their vapors in cold water containing a little stabilizing agent like ammonium nitrate. Fourth, by excess cooling. Colloidal solution of ice in an organic solvent like ether is obtained by freezing a mixture of the solvent and water. Article 7.6. Purification of colloidal solution. When a colloidal solution is prepared, quite often it contains certain impurities of electrolytes when are crystalloids in nature and tend to destabilize the solution. Hence, their removal is very essential. The following two methods are used for purification of colloidal solution. First is dialysis and second is ultrafiltration. Topic 7.7. Properties of colloidal solution. First, physical properties. A. Heterogeneous character. Colloidal particles being larger than molecules from heterogeneous mixture consisting of particles of dispersed phase and dispersed medium. The phenomena of Tyndall effect, electrophoresis and electroosmosis confirm heterogeneity of colloidal system. B. Stability. Colloidal cells are quite stable. Only a few colloidal particles of comparatively larger size may settle but very slowly. C. Fertility. Ordinary filter paper cannot be used for removing the dispersed phase because size of pores of filter paper is bigger than the size of colloidal particles which can easily pass through the pores of the ordinary filter paper. Animal membrane or parchment paper does not allow the colloidal particles to pass through it. These form the basis of separating the particles of the colloidal from those of the crystalloids in the process called dialysis, discussed earlier. D. Visibility. The particles in colloidal solution are not visible to naked eyes or under ordinary microscope. In fact, a particle is not visible with its size is less than half the wavelength of the light used to see it. Second, colligative properties, osmotic pressure. There are four colligative properties: osmotic pressure, elevation in boiling point, dispersion in freezing point, and relating lowering of vapor pressure. These properties depend upon the number of moles present. Colloidal particles have very average molecular masses and hence the number of moles present in solution will be extremely small. Thus, the value for any of the colligative properties for a particular substance will be smaller as compared to its value when it is a part of true solution. However, some colloids have measurable osmotic pressure, which have been determined with a reasonable degree of accuracy. Hence, osmotic pressure has been used to determine the average molecular masses of colloidal particles. Third, kinetic properties, Brownian moment. When viewed through an ultramicroscope, colloidal particles are seen continuously moving in a zigzag way. Robert Brown in 1827 observed such a movement of pollen grains suspended in water and hence it called Brownian movement. Thus, Brownian movement may be defined as a continuous zigzag movement of the colloidal particles in a colloidal sol. Cause of Brownian moment. The explanation of the phenomena is that molecules of a dispersion medium, due to their kinetic motion, strike against the colloidal particles from all sides with different forces causing them to move. However, colloidal particles, being comparatively heavier, move with a slower speed. Importance of Brownian moment. First, Brownian moment opposes the force of gravity and does not allow the colloidal particles to settle down. This is responsible for the stability of the colloidal solution. Second, it has also helped in the determination of Avogadro number. Fourth, optical properties, Tyndall effect. If a strong converging beam of light is passing through a colloidal solution placed in a dark room, the path of a beam gets illuminated with the bluish light. The path of Tyndall effect in 1869 and is called Tyndall effect. Thus, Tyndall effect may be defined as a scattering of light by the colloidal particles present in a colloidal sol. The illuminated path of beam is called Tyndall cone. The phenomena is also observed when the beam of light is projected in a cinema hall and it becomes visible due to the scattering of colloidal dust particles in the air of the room. A simple experiment as shown in figure 7.9 may be performed in the laboratory to see the scattering of light by a colloidal solution and distinguish between a true solution and a colloidal solution. The Tyndall effect has been used to devise an instrument called ultramicroscope in which the light scattered by the colloidal particles can be seen through a microscope. The importance of Tyndall effect lies in the fact that it has helped to confirm the heterogeneous nature of the colloidal solution. Fifth, electrical properties. A. Stability of colloidal sol, electrical charge on colloidal particles. The stability of a colloidal solution is due to the fact that the colloidal particles in the sol are electrically charged. The particles therefore repel one another and do not condense to form large non-colloidal particles. Colloidal particles carry either positive or negative charge. All the dispersed particles in a colloidal solution carry the same charge, while the dispersion medium has an equal and opposite charge. Using water as a dispersion medium, the charge on the particles of some common sols is as given in Table 7.5. Table 7.5, charge on particles of some common sols. Metallic particles, metal hydroxide like FeOH whole thrice, AlOH whole thrice. Starch, CrOH whole thrice, CaOH whole twice. Clay, oxides like TiO2, etc. Silic acid, hemoglobin. Metal sulfides like A2S3, CDS, etc. Basic dyes like methylene blue. Acidic dyes like Congo red, cosine, etc. Origin of electrical charge on colloidal particles. The various reasons for the origin of electrical charge on colloidal particles are as follows. First, frictional electrification. Second, electron capture. Third, preferential absorption of the ions from solution. Fourth, dissociation of molecules followed by aggregation of ions. Fifth, dissociation of the molecular electrolytes absorbed on the surface of particles. B. Electrophoresis or cataphoresis. The existence of the electrical charge can be shown by the process of electrophoresis, also called cataphoresis, which involves the movement of colloidal particles towards one or other electrode when placed under the influence of an electric field. The movement of colloidal particles under the influence of an electric field is called electrophoresis or cataphoresis. As soon as the colloidal particles reach the oppositely charged electrode, they get neutralized and coagulated. Electrophoresis can be used to find out the nature of the charge that the colloidal particles carry. Earlier the term used was khetraphoresis because most of the colloidal sols studied at that time contained positively charged colloidal particles and thus migrated towards cathodes. However, now the term electrophoresis is preferred because colloidal particles may migrate towards either of the electrode, that is, anode or cathode, depending upon the charge on the colloidal particles. It is interesting to point out here that when particles fall through water, a potential difference is set up. This is called sedimentation potential. It is the reverse of electrophoresis. This phenomenon was dispersed by Drawn in 1880 and hence it is sometimes known as Drawn effect. See electroosmosis. On placing a colloidal solution under the influence of an electric effect, the particles of the dispersion medium move towards a positively charged electrode, provided the colloidal particles are not allowed to move. This phenomenon is called electroosmosis. Thus, electroosmosis may be defined as a phenomena in which the molecules of the dispersion medium are allowed to move under the influence of an electric field, whereas colloidal particles are not allowed to move. It is interesting to point out here that if a liquid is forced through a porous material, example clay diaphragm or a capillary tube, a difference of potential is set up between the two sides. This is known as streaming potential. This fact is supported by the phenomena of electroosmosis. In fact, streaming potential may be considered as reverse of electroosmosis. D. Coagulation or flocculation. Coagulation is a process which involves containing together of colloidal particles as to change into large-sized particles which ultimately settle as a precipitate or float on the surface. Coagulation is generally brought about by the addition of electrolytes. When an electrolyte is added to a colloidal solution, the particles of the sole are attracted towards the ions which are oppositely charged and thus get neutralized. The neutral particles then start accumulating to form particles of larger size which settle down. Hardy squeeze law. The quality of the electrode which is required to coagulate a definite amount of a colloidal solution depends upon the valency of the ions having a charge opposite to that of the colloidal particles. This observation of Hardy and squeeze is known as Hardy squeeze law, which may be stated as follows. Greater is the valency of the opposite charge ions of the electrode being added, the faster is the coagulation. Thus, the coagulation of negatively charged aresus sulfide sole trivalent catalytes are far more effective than divalent cations, which in turn are more effective than monovalent. The minimum amount of an electrolyte that must be added to 1 liter of a colloidal solution so as to bring about complete coagulation or flocculation is called coagulation or flocculation value of the electrolyte. The smaller is the flocculation value of an electrolyte, greater it is coagulation or precipitating power. The coagulation or flocculation values of free electrolytes are given below. NaCl Na positive 52, KCl K positive 49.5, HCl H positive 30.8, MgCl2 Mg2 positive 0.72, BaCl2 Ba2 positive 0.69, AlCl3 Al3 positive 0.093. As coagulation power is inversely proportional to a coagulation or flocculation value, to compare the relative collecting powers of two electrolytes for the same colloidal sole, we have coagulation power of electrolyte 1 divided by coagulation power of electrolyte 2 is equal to coagulation value of electrolyte 2 divided by coagulation value of electrolyte 1. For example, for a coagulation of negative As2S3 sole, coagulation power of AlCl3 divided by coagulation power of NaCl is equal to coagulation power of NaCl divided by coagulation value of LaCl3 is equal to 52 divided by 0.093 is equal to 559. Thus, AlCl3 has 559 times more coagulation power than NaCl. For a negatively charged soles like that of As2S3, the coagulating powers of the cations are in order Al3 positive is then Ba2 positive, then Na positive. For a positively charged soles like that of FeOH3, the coagulation powers of the anions are in order FeCN6 for negative, then PO43 negative, then SO42 negative, then Cl negative. Coagulation can also be caused by the following methods. First, by electrophoresis. In electrophoresis, the particles of this first phase move towards a positively charged electrode and get neutralized. If the process is continued for sufficient time, these neutral particles unite and grow in size and settle down. Second, by mutual precipitation. Mutual precipitation is a process in which a positively charged soles are mixed in proper proportion to neutralize the charges of each other, causing coagulation of both the soles. For example, if positively charged ferric hydroxide and negatively charged arsenious sulfide soles are mixed, both the soles get coagulated. Third, by prolonged dialysis. The stability of a colloidal sole is due to presence of a small amount of the electrolyte. On prolonged dialysis, the electrolyte is completely removed. As a result, the colloidal sole becomes unstable and gets coagulated. Fourth, by heating or cooling. In some cases, heating the salt results into coagulation. Example, coagulation of butter. Similarly, in some cases, cooling the salt resulting in coagulation. Example, coagulation of milk, that is, coagulation milk fat starts floating on the surface. It is believed that the salt out effect depends upon the nature of the ion. The order of the cation is Mg2 positive, then Ca2 positive, then Sr2 positive, then Ba2 positive, then Na positive, then K positive, then Rb positive, then Cs positive. And the order of anion is citrate, then tartrate, then SO4 2 negative, then PO3 4 negative, then acetate, then Cl negative, then NO3 negative, then Br negative, then I negative, then CnS negative. This series is known as Hofmeister series, or more generally as lyotropic series. However, this order does not always hold good. The relative positions of the ions may change depending upon the nature of the colloidal being precipitating. Thank you.